In the previous video on response functions, we noticed that some of our response functions might involve taking the derivative of a potential with respect to one state variable and then the other. Since the derivatives of potentials are state variables themselves, this means that some derivatives appear to be connected to others in an unexpected way. Up here I've got the differential form, the fundamental thermodynamic identity for the Helmholtz free energy. Minus entropy times changes in temperature, minus pressure times changes in volume, and plus chemical potential times changes in particle number. This derivative identity gives us the equations of state. S is equal to minus df dt P is equal to minus df dv, and mu is equal to minus plus df dn. So those are all well and good. But what happens when we start taking second derivatives? If we take a second derivative of S with respect to temperature, if we take a derivative S, entropy, with respect to temperature, we get a second derivative of the Helmholtz free energy with respect to temperature, which is fine. We can't really say anything interesting about that, though. It's just some second derivative. If we take the derivative of P with respect to volume, same thing happens. If we take the derivative of mu with respect to n, the same thing happens. We just get these concavity or curvature values for the f function. But when we take the derivative of a state variable with respect to another variable that is not its conjugate, so a derivative of s with respect to v, or with respect to p, or with respect to mu, those derivatives will ultimately be related to second derivatives of the potential versus one variable and then versus a different one. Let me show you what I'm seeing here. If I set up a derivative of the Helmholtz free energy first with respect to pressure, and then with respect, first with respect to volume, and then with respect to temperature. Because f is an exact differential, and this is a legitimate function, f, underlying these derivatives, there is no difference in the order in which these derivatives are taken, right? Whether I do temperature first and then volume, or volume first and then temperature, does not matter. But these first derivatives here have meaning. So this seemingly trivial identity can be turned into a statement where if we first do the derivative with respect to temperature, we get negative entropy. And if we first do the derivative with respect to volume, leaving temperature for second, then we get negative pressure. In this situation, both of the negatives cancel off each side, but that won't always happen. And before we finish, let's make sure we know what variables are held constant. So this was S with respect to volume, while T and N were held constant. And this was P with respect to temperature, while volume and number were held constant. So this relationship here of second derivatives turns into something that doesn't look so trivial. What is this equation telling us? Well, these are both response functions of some type, and they can be thought of as experiments. On the right side, we're talking about a system that's held at constant volume, sealed so nothing can get out. And we add some heat to raise its temperature, and watch how its pressure varies. This derivative gives us essentially the slope of some graph. Pressure versus temperature at constant volume has some sort of behavior, and locally it has some slope. And that's what that experiment means, the measurement of the slope. But on the left-hand side, we have totally different variables. Here we're talking about an experiment where we keep temperature constant by allowing heat to flow in or out. We keep the number of particles constant by keeping it sealed. we expand or contract the system, maybe in a piston, and we watch how its entropy changes, how heat flows in or out. So in the left side of the equation, we're talking about a totally different experiment. We plot entropy versus volume. While keeping chamber sealed and allowing heat to flow in or out to maintain the temperature. And for a small region of volume variation, this graph will also have some slope. Now what this relationship states is that even though these two experiments are wildly different in terms of what apparatus is needed to set them up, what is measured and what is plotted, it's predicted that these two relationships will have the same exact slope. Slope of this blue line and the slope of this red line will be equal numerically and in terms of units. Extremely powerful relationship between two quantities that seem totally unrelated at first. These kind of relationships that come from mixed second derivatives are called Maxwell relations. They provide sort of shortcuts through thermodynamic identities that relate two quantities that are seemingly independent of each other. Notice that all Maxwell relations will follow a specific pattern. On the numerator of the left side, you will find a certain variable. Its conjugate will be on the denominator of the right side. On the numerator of the right side, you'll find some variable. Its conjugate will be on the denominator of the left side. The variables that are held constant on the derivatives will all be the same. TVN, TVN. For each potential then, here for Helmholtz we did one of these mixed derivatives. For each potential we can come up with many Maxwell relations. Let's do one more for the Helmholtz free energy. Consider taking the second derivative of F with respect to volume and then with respect to particle number. This should be equal to the derivative taken with respect to volume first and then particle number. So dF dN is mu. And on the right side, dF dV is minus P. So here is another Maxwell relationship derived from the fundamental identity for the Helmholtz free energy. And again, we have two wildly different experiments for the interpretation of each side. On the right side, we watch the pressure vary as we force particles into the system while keeping it at constant volume and temperature. On the left side, we somehow measure the chemical potential as we expand or contract the system, allowing heat to flow in and allowing the number of particles to stay constant. This Maxwell relationship also follows the pattern of having mu and n in conjugate positions and p and v in conjugate positions. Also, tvn are the variables that are considered independent. This Maxwell relationship ends up with a negative sign because of the negative in the formula for pressure relating it to a derivative. As you get practice with Maxwell relations, you can almost write them down just by inspecting the derivative equation. For example, there is one more that is not trivial. It will be d mu dt. From the definition, I can see that mu and t are not conjugate variables. So my derivative over here, I will expect to have n on the bottom, because it's the conjugate of mu. S on the top, right, because it's the conjugate of t. My signs are positive for mu and negative for s. So I'll have one minus sign here. And my natural variables in this case, are dV and N. So this, and this are the three standard Maxwell relationships for the Helmholtz free energy. Now there are other ones that we can write down. We can invert both sides of these. We can use maybe the chain rule on some of these to get something that looks like another Maxwell relationship. But usually you'll only need a few of these kind of once in a problem, and then that's all you need it for. Like I said, they're sort of like back road shortcuts from one description into another. For every other thermodynamic potential, internal energy, enthalpy, Gibbs free energy, there exists another set of Maxwell relationships. Let's see if we can practice figuring out what the Maxwell relations are that are derived from the enthalpy. Take a moment, pause the video, see if you can figure out one Maxwell relationship for enthalpy. Okay, let's write down the first one by being very explicit, following the method of a second derivative. Second derivative of enthalpy, what are our variables? We could choose any pair of S, P, or N. Let's look at the S dP first. Clearly this is going to be equal to the derivative dP ds. But dH dP is V. And dH ds is T. The natural variables are S, P, and N. So here is a Maxwell relationship derived from the enthalpy. It relates some strange quantities. How temperature varies with pressure as we hold entropy constant is equal to how volume varies with entropy as we hold pressure constant. On the left side, we're describing an experiment where we isolate a system, keep it adiabatic, and increase its pressure probably by changing its volume, and see how the temperature goes up or down. On the left side, we've got an experiment where we keep the pressure constant by allowing it to expand or contract. Changing its entropy basically means adding some heat. So we add some heat to an isolated piston that can expand and see how much it grows at a constant pressure. Those two derivatives are equal. For any potential and two variables, natural variables you want, you can derive a Maxwell relationship in this way. But we can also do it a little bit quicker by just looking at what are the natural variables and what are their conjugates. So here we have volume over entropy. So I'll expect that I have one more relationship that involves volume, not dV ds. That one was taken already. Not dV dP, because that is a pure second derivative, but dV dN. And the conjugates here of volume is pressure, and of number of particles is chemical potential. All terms come with a positive sign in the enthalpy, so we have a plus sign outside of both derivatives, and the natural variables are pressure, entropy, and number of particles. So there is a second derivative relationship, a second Maxwell relationship for the enthalpy. The third one will involve, I've already got one for volume and one for volume, so the third one will involve another expression with temperature on the top, and it's going to be the derivative with respect to pressure was already taken up over here, so dt, I could do dt ds, dt dp, or dt dn, right? dt dp showed up there, that one was done. dt ds is a pure second derivative. That's a heat capacity. So I'll have dt dn as my final Maxwell relation. So by the rule of conjugates here, I'll have d mu ds with the natural variables held constant. Okay, so these are the three Maxwell relations from the Helmholtz free energy. I'll leave it to you to work out the Maxwell relations for the internal energy and the Gibbs free energy from these examples. The ones for the Gibbs free energy are somewhat useful because pressure, temperature, and particle number are things which are often held constant in experiments. Now let's test some of these Maxwell relations for a system where we know some of the answers. I'm writing the equations of state for an ideal gas. And I'm writing these in the natural variables of the Helmholtz free energy, since we wrote down those Maxwell relationships earlier. I put everything in terms of N, V, and T. All right, so here's our pressure expression, here's our entropy, saccharotetrode, and here's our expression for chemical potential. Now let's test the three Maxwell relationships that were derived from the Helmholtz free energy. Do we remember what they are? One of them should be ds dv equals dp dt S and P are conjugate variables for Helmholtz. T, V, and N are the natural variables. The question left here, is there a minus sign? Well, volume is there as a natural variable. And volume is extensive. And that term normally comes with a minus sign. So pressure is there. Entropy is there. Temperature is there. So our expression for df, sometimes I just have to write this out just to remember. It's minus s dt minus v minus p dv plus mu dn. So both s and p have the minuses, so this comes out with no negative signs in the Maxwell relationship. Let's test this one. ds dv. Well, ds dv, v appears inside the logarithm there, so that's going to be equal to nk, basically nk over v. Right? All this other stuff is held constant, so it does not really do anything with the derivative. All right, so what about dp dt? Well, we're holding n and v constant, so it really couldn't be any simpler. dp dt is nk over v. Clearly those are equal, so that Maxwell relationship works out fine. Let's do another one here. D mu d t. All right, mu is a conjugate, so it's in the numerator. T is a natural variable, so it's in the denominator. And up on the top, then I'll have ds, conjugate of t, and down here, dn, conjugate of mu. All right, is there a minus sign? S has a minus in front of it, mu does not. So yes, there is a minus sign in front of there. and the natural variables are held constant. Vn, n, t, and v. Right. So what about d mu dt? Well, that one is kind of tricky, right? There's a t here and a t here. All right, so first I'll get minus k times the logarithm. And I'm not in the business of rewriting this logarithm too many times, so we'll just say minus k times the logarithm. That's our first term for this derivative. Then we've got a t inside of here, so we're doing essentially a product rule. We're going to have minus kt times the derivative of this logarithm with respect to t. So there'll be a factor of 3/2 if I can pull out front. It will be essentially 3/2 divided by t. So 3 over 2t will be the derivative of this logarithm. So if we put these together, then we've got minus k times the logarithm, and then minus 3/2 k. Very good. What about ds dn? Well, n appears two places in here as well, once in the front. So I'll have k times the thing in brackets. So the logarithm and plus this 5/2 factor. And then in my second term, I'm doing product rule between this term and the square bracket. So I'll have nk. And then the derivative of this logarithm. So the logarithm has constants divided by n. So that's going to basically give us a negative 1 over n. The derivative of a 5/2 is, of course, 0. So that's our expression for ds dn. Let's simplify that a little bit. I see first here I have k times the logarithm. And then I've got plus 5/2 k, and then the n's cancel here. So I'll have plus 5/2 k minus k. So that's going to give us a plus 3/2 k. And what do you know? This derivative comes out to be exactly the opposite of d mu dt. So these Maxwell equations, Maxwell relationships, seem to be verified, at least in this model. Now there's one more thing we can learn from the Maxwell relationships, and it has to do with how variables are extensive or intensive. Let's write out a Maxwell relationship for the given for energy quickly. dg is minus sdt plus vdp plus mu dn. I just chose Gibbs free energy for fun. Let's write out its Maxwell relation for ds dn. ds dn will be equal to d mu conjugate of n over dt with a minus sign in front because there's a differing sign between these. And the natural variables held constant are n, t, and p. So that's the Maxwell relationship. But notice what we can tell here if we consider whether these quantities are extensive or intensive. Remember that since mu is an intensive quantity, if it is expressed in terms of only other intensive quantities, then no extensive quantities can appear in the formula for mu. So if I write mu as a function of t, p, and n, no n's will appear. That means mu is essentially a function of only t and p. And this derivative then takes that derivative with respect to the temperature term. no n's appear in the derivative, so I don't even need to specify that n is held constant. This result is going to be some function of kin p alone. I'm writing this function as a lowercase s for a specific reason. Because of the Maxwell relationship, we know that this d mu dt with a minus sign in front is equal to ds dn. And I really want to emphasize how small this s is here. It's a different function. It's dependent only on temperature and pressure. Now, what does this kind of equation means? It means that if we have the extensive formula for the entropy and take its derivative with respect to n, while it's expressed in terms of temperature, pressure, and n, that the result is independent of n. If we just think mathematically, if I take the derivative of a function and it equals a constant, then it means that that function must be simply equal to the constant times the independent variable, right? It's just a line. So that means that we can conclude from this that the entropy, written as a function of particle number, temperature, and pressure, must be equal to the number of particles times a intensive function of only temperature and pressure. This means that the dependence of entropy on number of particles is trivial when it's expressed in terms of temperature and pressure. We can do similar things for most of the other extensive variables we find. The volume, expressed in terms of number of particles, temperature, and pressure, must be equal to the number of particles multiplied by some intensive function of temperature and pressure. And we'll find this is true for any thermodynamic model we can cook up. If we express it in terms of n and intensive variables, then the n can only exist as a multiplying factor that makes it scale correctly.